So today we're going to go over Maxwell equation without using calculus, right? So when we talk about Maxwell equation, we talk about the Gauss law 1, Gauss law 2. We talk about the Maxwell equation 3, which is the Faraday's law of induction, and Maxwell equation 4, which is also known as Ampere's law. Okay, so everything you're going to do without using calculus. So let's write down all four Maxwell equation. And number one, these are the Maxwell equation. Why Maxwell equations are important? Maxwell equations are important because before Maxwell, before 1867, used to be electric force and magnetic force are two different phenomena, like gravitational force, strong nuclear force, and weak nuclear force. Now we no longer consider electric force and magnetic force two separate phenomena. They are known as a single phenomena, which is electromagnetic force, thanks to Maxwell. James Clerk Maxwell. He put them together by using four equations. I just mentioned them: Gauss equation 1, Gauss equation for magnetic field, Gauss equation for electric field, Faraday's law of induction, and then Ampere's law. You put them together, he gets something. Which is the speed is or electromagnetic waves is 1/square root of mu times epsilon, which is 3 times 10 raised to 8 meters per second. Okay, we're going to get everything without using calculus. So at least we're going to try not to use calculus. Okay, so Maxwell equations. Number one, we're going to use the Gauss law for electric field. Gauss law for electric field is we're going to start with flux. Electric flux is equal to E for electric field, A for area, cosine theta. Number two, Gauss law for magnetic field. Gauss law for magnetic field. Magnetic flux, magnetic field, area, cosine theta. Number three, Faraday's law of induction. Faraday's law of induction tells us something like this. Sigma, again, we're not going to use the calculus. Sigma magnetic field delta L is equal to mu naught times current. And then finally, we're going to write down Ampere's, this one is Ampere's law. Faraday's law of induction is this. EMF is equal to negative n. Negative is the Lenz's law. Negative n flux divided by delta T. And the number 4 is Ampere's law. Ampere's law. So Ampere's law, a few seconds ago I wrote it, sigma magnetic field times delta L is equal to mu naught times current. Okay, let's understand Ampere's law, because Ampere's law is the easiest one over here. Let's consider a wire. Okay, in 1820, Hans Oersted discovered, after he putting the current in the wire, let's say current moving to the north, he discovered the current carrying wire create a magnetic field around it, which is counterclockwise. The field goes inside and come outside. So yes, magnetic field is counterclockwise. So let's write magnetic field. So this is, you can think of cross section of a cylinder. When you take a scissor and cut a cylinder, what do you get? You get a circle. So if you put together infinite number of circle, one on top of each other, you get a cylinder. Okay, now when you talk about circle, what is the geometric property of circle? It's made of loss of point equidistance from the center. All right, 2 point altogether you can delta L. Okay, so delta L is there, come from the circle created by the current carrying wire around the wire. Now, this is not the entire all the point on the circle. This is just 2 points, L1 and L2. If you want to put all point on the circle, you have to put sigma. What type of circle it is? It is a magnetic field, which is equal to permittivity. No, all this is not permittivity. This is very close to permittivity. This is permeability. Permeability of a free space. Current times current. Permeability of the free space is 4 pi times 10 raised to negative 7 Tesla meter over ampere. Okay, this is a constant. It's very important. We're going to get to see it in a second. However, this is magnetic field. So magnetic field is this one, you can replace it by 2 pi r. Okay, because this is 2 pi r. All the point is 2 pi r. That's all the point on the circle. So the magnetic field is mu I over 2 pi r. So that's where the Ampere's law comes from. Okay, very nice. Ampere was the one who invented the current in 1820, and Hans Oersted, he discovered the magnetic field in 1820 as well. Okay, now let's try to understand flux. What is flux? If I have a piece of paper, which I don't, maybe seems like I don't have any piece of paper. Do you have any piece of paper, Isaac? All right, I have napkins, but napkins will work as good. So let's say you can think this is a plane, because it is. Now, if there is a rain and you don't have umbrella, you can block the rain by holding it like this. And let's talk about myself. What is myself? Myself is standing perpendicular with respect to the plane, which is a section of the earth, right? So the ground. Okay, if there is a rain, what is the raindrop direction with respect to the ground? Perpendicular. What is the raindrop direction with respect to myself? Parallel. So now this plane, can you imagine a normal line? Normal line is the perpendicular line coming out from the plane. If there is a rain, what would be the rain with respect to the normal line coming out from the plane? Parallel. So this concept will allow us to understand flux. What is flux? Flux is flux measures the field passing through a surface. Okay. So let's consider first magnetic flux or electric flux. So the flux measure the field passing through the surface. So this is a surface, this is a plane. So you're going to draw a normal line with respect to the plane. We're going to draw 3 plane, normal line with respect to the plane, and normal line with respect to the plane. So we're going to represent the magnetic field. This will represent electric field. This will represent the magnetic field. Again, this is the normal with respect to the surface, normal with respect to the surface, normal with respect to the surface. Now this one, if this is the magnetic field could look like this. I'm going to show you 3 extreme scenarios. This is another extreme scenario. This is another extreme scenario. This is normal. This is normal. This is magnetic. This is electric field. This is electric field. This is electric field. This electric field, as you see, is parallel with respect to the normal. Now, when the electric field is perpendicular with respect to the normal, then what is the electric flux? Electric flux is 0. When it is, let's say, 30 degree with respect to the normal, then electric flux is EA cosine 30. When it is parallel with respect to the normal, then electric flux is just EA 100%. On the other hand, you have the magnetic field, perpendicular magnetic field 45 degree, magnetic field parallel. Magnetic field over here, magnetic flux would be 100%. Magnetic flux would be, I don't know, 45 degrees. So magnetic flux would be BA cosine theta. And magnetic flux would be 0, right? Because it's perpendicular with respect to each other. All right, so this is the idea, magnetic flux. Very easy idea, but it's very powerful tools. Okay, so we're going to use this to measure electric flux and magnetic flux. So let's do the electric flux. Let's consider a charge. This is a sphere. All right, this is an electric monopole. This is a sphere. Let's say this is 50 microcoulomb. We try to find the electric flux. Okay, and let's say this sphere has a radius which is 4 meters. The sphere volume is 4/3, I believe, r cube. If you take the derivative, which we don't want to show, we're not going to do any calculus, forget about it. The surface area is, I believe, 4 pi r squared. Okay, now let's do the flux. So what is electric flux? Electric flux would be EA cosine theta. The normal and electric field is 0 degree because they are parallel. So we have electric field is EA. What is E? KQ over R square. What is A? 4 pi R square. That's the surface area of a sphere. R square cancel. If QE is equal to KQ 4 pi. What is K? K is 9 times 10 raised to 9, which is 1/4 pi epsilon. So K is 1/4 pi epsilon. Don't forget the Q, and don't forget 4 pi. 4 pi cancel. QE is equal to Q over epsilon. Q is a 50 microcoulomb, and epsilon is, this epsilon is 9 times 10 raised to 12. So 9 times 10 raised to negative 12. So this is 0. I don't know how much. 9 goes to 50, 5.6. 5.6 times 10 raised to 6. I'll look like it. 10 raised to 6. And this is Newton. And then meter square over Coulomb. Okay, this is how you can find the flux. This is electric flux, and then let's go over an example of a magnetic flux. So this one was electric flux. Let's go over a magnetic flux. Okay, so how are we going to do magnetic flux? We're going to do Gauss law for magnetic field. So we're going to find magnetic flux. Let's consider a loop. One loop. One loop is created by a wire. So wire has a resistance. So that's 20 ohms. Loop means circle. It has a radius. So loop radius is 0.25 meter, 25 centimeters. Loop has field. Let's say the field, initial field is 1.5 Tesla, and final field is 4.8 Tesla. And let's say these change happen in 0.023 second, 23 millisecond. What we want to find is magnetic flux. So what is magnetic flux? Magnetic flux is, of course, BA cosine theta. This is normal, and our B field is also parallel to the normal, so that we can say BA, because cosine 0 degree is 1. Then we can conclude that B is 4.8 minus 1.5 is 3.3. Pi r is squared, 0.25 is squared. So this is 0.65 Weber. Weber is the SI unit for magnetic flux. All right, so what are you going to do now? EMF. We have EMF over here. EMF is induced voltage. Induced voltage. So EMF is negative N flux over T. Loop is 1, negative 1. Magnetic flux is 0.65. And the time is 0.023. 28 volt. SI unit for voltage is a volt. SI unit for EMF is also volt, because EMF is a special case for voltage. This is induced voltage. Let's find the current. To find the current, this is called induced current, VIR. So current is voltage over R. This is not voltage, this is EMF. So EMF over R. So 28 over R, which is 20, 1.4 amps. So the current flows in it is 1.5 amps. All right, that's the Faraday's laws of induction. Now finally we're going to do Ampere's law before we put them together. This is Maxwell equation without using calculus. All right, so Ampere's law, what are you going to do? We have a 4 scenario. One scenario, the current moves to the north. Second, current moves to the south. Third, current moves to the east. Fourth, current moves to the west. All four scenario, we're going to try to find the field 2 centimeter, 2 centimeter, 2 centimeter, 2 centimeter. You're going to call location A, location A, location A. You're going to find the field at location A, which is 2 centimeter from the wire that carries the current, create the field. Scenario 1 is going to create, if you use right hand rule, thumb at the direction of the current, you curl your finger, go in and come out on the other side. So this is counterclockwise. And the field would be, this is counterclockwise, and the field would be mu current 2 pi r. Mu would be 4 pi times 10 raised to negative 7. Current is 45. 2 pi, r is 0.02. Pi cancel. This goes to 100 times. You have 4.5 times 10 raised to negative 4 Tesla into the pace or counterclockwise. This one, magnetic field is 4.5 times 10 raised to negative 4 Tesla out of the pace or clockwise. This one, let's do 45 so I don't have to do the math. Trying to be lazy over here. So this one going to be clockwise. Why this is clockwise? So this is in, this is out. Okay, so this is going to be clockwise. So the field over here is going to be same thing, 4.5 times 10 raised to negative 4 Tesla. Or we're going to say outward or clockwise. As you see, outward is always clockwise. Into the pace is always counterclockwise. All right, we're going to place our thumb at the direction of the current. We're going to curl our finger. So this is counterclockwise. The size of the field over here, since the current is same, is going to be 4.5 times 10 raised to negative 4 Tesla. This is inside the board or counterclockwise. I gave you the example of each and every Maxwell law. There are 4. He put together these 4 equations, and this gave him the speed of light. So if you look carefully, you're going to see over here in this one you got epsilon, which is 9 times 10 raised to negative 12. And this one you have mu, which is 4 pi times 10 raised to minus 7. We're going to get to see what they can do to us. Okay. All right. This one and this one. So this is electromagnetic. So you're going to say E. This is magnetic. This is also magnetic. This is also magnetic. So you're going to say M, EM waves. E for electric field, M for magnetic field is actually B. But we simply going to say EM waves. All right. So E look like, all right, so you're going to get to draw it. You're going to draw E field, which is up and down. Why it is up? Let's try to understand that. Let's put a charge over here, put a charge over there. The field is up. Okay. Two plate, positive plate, negative plate, and so two charges, they move. So at some point, if they move up and down, at some point they will be at same height, and the field would be zero over there. So positive and negative, height is zero, so field is zero. Over here, negative, positive, so field is down. Over here, positive, negative, height is same, so field is zero. Over here, positive, negative. All right, so now you know why electric field is up or down. Now you're going to get to see the magnetic field. Where does that magnetic field come from? Equation number 4. A wire that carries current goes inside and come outside. That's counterclockwise. Thus creates the magnetic field around the wire that carries current. So in and out. So how can we draw in and out? We're going to go to the Z component. All right. So this is out. You're going to draw it out like that. This is out. This is out. This is in. This is in. This is in. So what I actually did try to do is this. If I have a pen, I do. Okay, I have a pen and I have this eraser. So this is the direction of the electric field. This is the direction of the magnetic field. That's not how I draw it, but that's how you should see it. Now I'm gonna change the direction. Okay, it was like this before. Now it's gonna be like what? Now this is gonna be like this, and this is gonna be like this. Okay, like this. Okay, like this. Okay, inside the board. Now the blue one is electric field. The red one is magnetic field. Magnetic field associated with permeability. The electric field associated with permittivity. Okay, and this is called EM waves. So when you put them together, EM waves, you get 1 over epsilon and mu. Epsilon is, what is epsilon? Epsilon is 9 times 10 raised to negative 12. And mu is 4 pi times 10 raised to negative 7. This is 3 times 10 raised to 8 meter per second. And this is Maxwell use a letter to represent this value, and this is c. This is the speed of light in the vacuum. That doesn't mean light cannot move in other medium. It does. It does move through other medium. However, when the light moves in the vacuum, it is 3 times 10 raised to 8. When light moves in the air, is also 3.10 raised to 8, because air and vacuum are kind of same, because index of reflection for air is also 1. However, if light moves in the water, is going to be probably 2.25 times 10 raised to 8, much less than 3 times 10 raised to 8. Okay, so as you see that Maxwell used this equation to get to the electromagnetic waves, and electromagnetic waves has a speed which is the speed of light. So electromagnetic wave itself is light.